Hi guys, welcome. This is module CM3292 and it's one of the mini e-lectures on ion chromatography and is linked to experiment 1A. Rather like the other e-lectures, the structure is given on this slide. I need to talk a moment about references. Skoog et al., a good solid analytical textbook. It has many of the tools in it. It doesn't particularly cover ion chromatography very well, but nonetheless it's here simply because of all the other things it covers. The Harrison reference does a competent coverage of ion chromatography and certainly covers what we're going to be talking about in this lecture. But if you want real detail, the Dynex company, who manufacture ion chromatographs, and no, I won't make a statement about how good or bad they are, but they do have an excellent range of reference notes, over 100, and you can get these just by typing Dynex reference notes into Google. Very much recommended, rigorous method development notes, and we'll leave that there. So, onward and upward. As with the other mini lectures, the aim of this lecture is not to brief you on the practical per se or the equipment. You've got videos that will show you how to start the equipment, run it, do the analysis, take the data off and shut the equipment down. So it's not about the operational equipment. You've got laboratory scripts which tell you what you need to be doing in the laboratory and things like that. So this e-lecture is not about that either. What it is about is the underlying theory of the equipment and, to a small extent, the techniques you'll be using. When there are particular things that you are going to be doing, I will mention them here. So, for example, in Practical 1A, you'll be using anion ion chromatography, and therefore most of this lecture will be about anion ion chromatography. Practical 1A comprises 3 mini lectures, this one on ion chromatography, a second one on sampling, and a third one on auto-analysis trains. Right, okay, so ion chromatography is a specialized form of high-pressure liquid chromatography, a technique you've covered in the second year in CM3192 Analytical Chemistry, and again in the second year practical module CM3192. I'm not going, therefore, to dwell on those basic elements of theory which you already covered. The previous work you've done covers the advantages and disadvantages of HPLC with respect to, for instance, gas chromatography. And similarly, ion chromatography shares some of those advantages and disadvantages. I won't be talking about plate theory, for instance, because you've already dealt with it, and it applies equally to HPLC in the second year, to ion chromatography in the third year. It's a low flow rate, high pressure method, but whilst it's high pressure, it's not as high as HPLC. The main reason for this is that most HPLCs use steel plumbing, so that your eluent, your mobile phase, is running through steel, so you can pump to very good pressures, and then that gives you the resolution, or some of the resolution that you get in HPLC with low flow rates. With ion chromatography, with the type of elements you would be using, you would actually corrode the steel, dissolve the steel, in fact. So instead, all of the tubing inside an ion chromatograph is made from PEEK, which is a polymer, and it means that the pressures aren't quite as high as those you might find in HPLC. Other differences, the column structure. In ion chromatography, the columns are unidirectional. So in HPLC, you might back pump a column, that is, pump the eluent in the opposite direction to that used during the analysis to clean the column. You can't do that with ion chromatographic columns. They're packed in such a way that that would actually rupture the column. The column packings are different. In ion chromatography, you're using ion exchange resins effectively, and the detection is different. Now, in HPLC, you in the second year used UV-Vis detection. You could use in HPLC conductivity detection. In ion chromatography, you use conductivity in the main, that's the workhorse detector, but you can also use a variety of electrochemical techniques as detectors: cyclic voltammetry, cathodic stripping voltammetry, a whole tranche of them. And finally, you also use, with ion chromatography, eluent suppression, and we'll talk more about that in a moment. Okay, summary description. I did try to write stuff, but in the end, it seemed much better to actually draw you a diagram. Across the bottom are the basics of the method flow, which you could, some of these things you could write for HPLC. Injection, you need to get the sample into the system. Separation, now so far that's both fine and dandy for HPLC. The next stage in ion chromatography is suppression, followed by detection. And then there's a recycling loop, which we'll talk about later. So let's go through the diagram and see how it works. So like an HPLC, you have a high pressure pump, and you have, in this particular incarnation of ion chromatography, you have pure water running through that pump. You then have an eluent generator, which is an electrochemical device, which also has chemical cartridges, and that basically produces your mobile phase or your eluent for the analysis. We then get to injection, and the separation takes place on a column, rather like HPLC, except this column is composed of an ion exchange resin bed. At which point, after the separated sample of a sample stream with the ions separated leaves the column, it goes through suppression, where the background conductivity of the eluent is suppressed, and then goes through the detector, and we have the various data outputs. Okay, a bit more detail then. Let's think about how each part of this system works. So, ion exchange resins, we're dealing with anions, and so I'm only really going to talk about anions, but I could equally talk about cations. The resins will be different, and obviously the chemistries are different, but the fundamental concepts are the same. Okay, so we have a resin bead, which is on your diagram, and you have substituted aldehyde groups around as part of the resin, and these are protonated, so you've got multiple groups on them, and they are charged, so that you have a positive charge on the nitrogen and a negative charge on the hydroxide anion. Clearly, let's imagine that we have a sample with chloride in it, shall we say. The way this works is the eluent containing the sample is pumped through a bed of these resin beads, and the chloride is taken up on the resin, and the hydroxide ion is displaced by that chloride. Now, the fundamental basis of this separation is the so-called selectivity coefficient, because of course there's an equilibrium between the hydroxide ion on the resin and the chloride ion in the sample, and that equilibrium is sketched out here for you. One can think of this thing as all of the time, once you have your sample ions on the column, the eluent anions, which are typically hydroxide, are then competing with those absorbed chloride ions, and eventually they will displace those absorbed ions because there are so many more of the eluent ions than there are sample ions. But anyway, we'll get to that in a moment. So, selectivity coefficient, that's the basis of our separation here, and if we were to put that mathematically as chemists, we would have basically the hydroxide ion in the mobile phase multiplied by the halide ion, in this case it's chloride, in the stationary phase, divided by the hydroxide ion in the stationary phase, and divided by the, in our case, chloride ion in the mobile phase. So, by using the selectivity coefficient, this is how we actually establish how good a separation system we've got, and we'll talk more about that in a moment. What are the factors that affect the value of K? Not the chemical factors particularly, but the nature of the ions. Okay, well there are three: the charge on the ions, the size of the ions, and the polarizability of the ions. So I'll go through each of those three briefly now. Basically, the higher the valency of the analyte ion, the longer the retention time. So nitrate has a single negative charge on it, sulfate has a double negative charge on it. So the retention time of sulfate is longer than nitrate. Obviously, if you look at the formulation of K, the pH is important, but that's something that you can determine. Okay, so charge is fairly easy. The higher the charge, the more sticky, in inverted commas, it is, the more it's held tightly, it's held onto the resin. Size. The larger the radius of the analyte ion, the larger the retention time. So this series of halogens, iodide will have a much longer retention time than any of its lighter halide companions, and in fact the elution order is as below. So the residence time increases with retention time. And finally, polarizability. The more polarizable an analyte ion is, the longer the retention time. So we already know that if we were to compare chloride, which is single valent, and sulfate, which is divalent, the sulfate would have the longer residence time. But if you were to compare thiocyanate, a single valent ion, with sulfate, a doubly valent ion, because thiocyanate is much more polarizable than sulfate, in fact, thiocyanate has the longer residence time, the longer retention time. So for any single analysis, all these three effects are superimposed on each other to give you the ultimate elution order, which of course you can tailor. That's the whole point. You may choose one type of eluent or another type of eluent to get a particular elution order that your sample ions will allow because of the composition. Okay, so charge, size, polarizability, they're the basics of the separation, or really the basics that underlie K. Things that you need to do a decent ion chromatographic separation, things that you need to do a good ion chromatographic separation. The pH needs to be stable. Now that's obvious in one sense, simply because of, if you remember, hydroxide appears in the equilibrium constant. So the way that's dealt with is the use of polymeric anion, in this case, exchanges, and we'll talk more about that in a second. High chromatographic efficiency. So we need to reduce the diffusion effect. In chromatography, it's also called the Gaussian effect, the spreading effect caused by diffusion. You may remember in the second year, you did a gas chromatography experiment where you actually examined this. That needs to be minimized, and we need to maximize mass transfer between the mobile and the stationary phases. And we do that in this technique, and that's how we get such high chromatographic efficiencies. Again, more of that in a moment. Different selectivities. It all hinges on the selectivity coefficient, the equilibrium constant, but effectively we have a number of different ion exchange functional groups we can use, which gives us different selectivities for different ions. So we need to choose the appropriate functional groups or mixture of functional groups for the separation that we want to do. Finally, solvent compatibility. The base polymers that form the backbone of the ion exchange resins have a high degree of cross-linking. We're putting aqueous solutions for anions at any rate at high pressure through these beads, so we want as little swelling of the resin as we can get, as fewer shrinking effects as possible when we have to chop and change the solvent. Bear in mind we're talking about anion ion exchange here. If we were talking about cation ion exchange, then we would be using non-aqueous solvents. But as I say, we're not really going to talk much about that in this eLecture. Other things we need to think about: the mobile phase. If we want pH stability, we could use a buffer. And in fact, in your practical, you're going to be using a buffer as the mobile phase, which makes pH stability much easier to realize. You don't have to use a buffer, however. Typically, potassium hydroxide is an element which is used for anion separation. And the stationary phases, there's a number of different factors here: the ion exchange capacity, the functionalization or the mixture of functionalization that you use, and these are commercially available, so one just needs to look them up, and different resin bases and strategies. I'm just going to pause there for a moment and look at a couple of those very lightly. There are three basic developments in anion exchanges, three strategies, if you will, of design. The first is on the left of your cartoon. it says nanobead agglomerated. How that works is actually you have a resin core, which can typically be styrene, divinyl, benzene, copolymers. There's a list of resins at the bottom of the slides, and they can be used, they can be mixed and matched with these strategies. So basically that resin core is sulfonated, and then we use nanobeads with amine groups or substituted amines, which then effectively sorb onto the surface and are fairly fixed on the surface, and they provide a very high surface area, anion exchange resin. You get the advantages of using nanobeads with their extremely high surface area, but the mechanical strength of the larger core particle. And some resins are still made that way, but they've somewhat been overtaken by two other devices. The first is grafted surface aminates, and you have there a bead, and you can see inside that there is a large surface area in there of pores and cracks. So effectively it's a high surface area, and it's an aminated surface, so it has again amine groups in there to interact with the mobile phase. Finally, there's hyperbranched anion exchangers. You can imagine this as a woodland with trees growing on it. So your eluent, your mobile phase, never ever gets to interact with the actual polymer surface. It reacts with the exchange sites on the inverted commas trees, on the branches that come up from the surface. So the surface is covered with these sites, and that gives you actually, because you then don't have to worry about interaction with the surface of the bead, all of the chemistry happens on the inverted commas trees, and those you can design quite specifically. Okay, so we've talked quite a lot about the separation. Let's now talk about the detection. A standard conductivity cell, you have a positive and negative electrode, and when you apply an alternating voltage between those electrodes, the alternating current between those electrodes, the positive ions move toward the negative electrode, and the negative ions move toward the positive electrode. Note, you use alternating current, because if you use DC current, then you start getting electrolysis, which you actually don't want. But let's think a moment about the system we've got here. So we have the effluent from the column, which is typically millimolar in maybe carbonate or bicarbonate, which is what you'll be using, with maybe ppm or ppb sample. So a ppm is micrograms per milliliter, a ppb is micrograms per litre. So clearly conductivity is proportional to the relative amounts of ions. You're going to have a huge background signal from the eluent and tiny little bumps which represent the tiny amounts of analytes that you're actually interested in, which leads us to suppression. Some types of ion chromatograph still don't have suppression technology, and effectively they have a huge signal to noise ratio, a very low signal to noise ratio, a bad signal to noise ratio with a very high noise level or a very high background and a relatively low signal. The sort of ion chromatograph you'll be using, and others like it, actually suppress the conductivity of the eluent before detection. So effectively, the background from the eluent is converted to weakly dissociated species, while the analyte signals are enhanced for fully dissociated species. So this increases the overall signal to noise ratio. Let's look at the chemistry of how that happens now. In terms of the technology, the suppressor capacity is massively more than any reasonable eluent that you would use. And for anion analysis, with actually the bicarbonate eluent that you'll be using, the sodium carbonate in the eluent exchanges with hydrogen ion from the suppressor resin to form so-called carbonic acid, which then dissociates into carbon dioxide and water. For the analyte ions, the things you're interested in, let's imagine we've got a sodium halide there, then again the sodium chloride, shall we say, goes into the suppressor column, and again the hydrogen from the ion exchange resin exchanges with the sodium, so the sodium stays on the resin surface, and what leaves the column is the hydrogen. A hydrogen, if it's chloride, it would be HCl. Now you may remember from your physical chemistry about transport numbers and about the higher transport numbers of things like HCl over NaCl, because the acid salts are for good reasons and to do with proton transport have a much higher conductivity, have much higher transport numbers. But I'll leave you to look that back up in your notes. Okay, now technologically I'm not as interested in this. The suppressor you'll be using actually splits water to supply regenerant ions, and obviously the water splitting reactions are here. That allows you to do an ion balance across the detector and is also a source of pure water. I'll show you how that works now. So this is diagrammatic, and in the extremes of the diagram you have the anode and the cathode, and along both of the anode and the cathode you have water flowing, pure water. The two golden bars are actually cation exchange membranes, and your sample in the eluent, and in this example it's sodium hydroxide, is running through from the top of the diagram to the bottom. So this is a counterflow system. In the old days it actually was a column and you had acid that flowed one way and your sample flowed the other, but now it's somewhat more compact. So let's look at the fate first of all. On the anode you have water being electrolyzed, which is producing hydrogen ions, which diffuses through the left-hand cation exchange membrane, which is fine, into the sample flow. So in your sample flow you have sodium hydroxide as an eluent, and you have sodium and X- as your analytes. So the first thing that happens is you then have your hydrogen ion from your electrolysis of water actually reacts with the hydroxide ion from the eluent to form water, which has of course a very low conductivity. The sodium ion, on the other hand, which is left, can then move through the cation exchange membrane on the right and is then taken up by the hydrolysis products, the OH minus hydrolysis products of the cathodic decomposition of water on the right hand side of your slide. Likewise for your analyte, if it's in there as, shall we say, sodium chloride, then by exactly the same reaction it ends up as hydrogen chloride, HCl minus, H plus Cl minus, and the sodium that was associated with your analyte chloride again goes through the membrane on the right and is suitably disposed of. Actually, it's recycled, but that's technology we don't really need. But you can see that what went into the suppressor was your, should we say, sodium chloride in a sodium hydroxide eluent rather. What comes out is all in pure water, and you just have, in this case, HCl. So now, rather than looking at detecting a tiny amount of sodium chloride against a huge sodium hydroxide background, you're actually detecting HCl has a greater conductivity than NaCl against a pure water background. So you've both increased the conductivity of the analyte and decreased the conductivity of the eluent. So it's like a double whammy. And for completeness, here are the suppressed products for the sodium bicarbonate and sodium carbonate, which is what you'll be using. And the elution strength, the flexibility you have, actually goes up on this list. Okay, I can let you read that, I think. So, closing summary, I've decided probably chromatograms are the easiest way to show you this. These are all suppressed conductivity, so they work in the way we've just described, and the sample is a mixture of those 8 analytes: sulfate, phosphate, nitrate, bromide, nitrite, chloride, acetate, fluoride. In your practical, you're going to be looking at nitrite. And you can see that the different types of ion exchange resin with the same eluent give you sharper or less sharp peaks depending on what you're actually using. Clearly, you are using a resin which is giving you very sharp peaks, which gives you high chromatographic separation. But that's really something that I'm not really going to talk about because you've talked about it in your previous work. Okay, that's just a very brief introduction to ion chromatography. I think probably I've said what I need to do. So thank you for listening and enjoy the practical. Good night.